morning, everyone. I'm Dania.
My name is Manuel.
And we are the MethaneHydrateCombustion team.
To get started with, I'll give you all a quick brief background about our project, which is MethaneHydrate. Methane hydrates they're located in the sea, deep down in high pressure, low temperature areas. And they're currently being studied because it is unknown on how the combustion properties are, and there are certain laboratories that are doing certain combustions on them in ideal states. And the bigger picture of methane hydrates is that there's an abundance of them in the ocean. There has been research from the University of Texas that there's enough methane hydrates to combust for 250 years. So there are, of course, it's a very interesting topic just because once we learn how to fully combust it in ideal states, then we'll be able to, of course, use it. And our goals and objectives for our project is building a chamber in an ideal state with laminar flow of air going into the chamber and having uniform airflow within it, and also measuring the methane hydrate in terms of weight loss of the methane hydrate and as well as water vapor, just because methane hydrates are a crystal lattice with water and methane hydrate combined. And we want to make sure we're doing this with a Interact 700 to measure the emissions of the methane hydrate.
So now that we've given you a brief background of our goals and objectives, we're going to segue into our organization. So basically, last quarter we had 3 subsystems: the emissions, mass loss, and the airflow. And each of these subsystems would go into the different types of components that we are looking to analyze. So, for example, emissions has combustion testing, which we will perform or have performed, and analysis of the reliability of this machine. We will also go into data analysis, and with all of these components, we'll be able to write a standard operating procedure. And this is similarly for the 3 other subsections. This quarter, we added in a systems subsection because last quarter we were in the design phase, and this quarter we are implementing everything together. So we're in the process of fabrication. So we integrated airflow, emissions, and mass loss all into designing this combustion chamber. And we did take into account that there might be design problems, so that's where systems comes in hand, where they will look at the schematic of the diagram and implement different engineering principles to fix these design problems and write a standard operating procedure for those issues.
And for our timeline, as you can see, as we're in winter quarter, we're able to submit our project specification that entails all our equipment and materials that we'll be using, as well as our current current status with our test chamber. And since we are in week 7, we are now in the works of finalizing the manufacturing and assembly document, and later on we'll be getting into our safety document. And for our milestones, last fall quarter, since we did submit our project specification, that was in the work last quarter, and that's a milestone because we were fully able to document and detail how every equipment will be utilized in the test chamber. And our second milestone was that with our first milestone being completed with our specifications, we used that to make simulations on SolidWorks to figure out how the uniform airflow will be in our test chamber. And now with those 2 milestones completed, our third milestone as of this quarter is to finally test the chamber with everything in sync.
Okay, so for our progress right now, as Manny was saying, we are in the process of testing our combustion chamber. So we did have SolidWorks schematics, as you can see here. This is our mass loss system. It includes strain gauges that will measure the weight of the sample, of the fuel that we'll be placing on here, on the mesh. And then, in addition, there's an airflow system that will provide air into the airflow into the combustion chamber as seen here. And as you can tell, we also have gel ethanol, which is our fuel one of our fuels. It's a substitution fuel for methane hydrate because it has similar properties and it's readily available. So we use that in order to get data analysis. And so this is the mass loss system with the gel ethanol on it, and the airflow system is connected through piping right there. And the NRAC emissions probe will be placed on top of the combustion chamber to provide data analysis. And the reason why we need these SolidWorks schematics for this combustion chamber is because, again, when there's design issues, we'd like to go back and go into these SolidWorks schematics and reiterate them in order to kind of visualize how, if we make any changes, what it would look like, and perform simulation testing to ensure that it would work. We have a way of validating that it would work analytically or theoretically first, and then actually going in and making these design changes. This is our actual methane hydrate, and it's it's ignited here, and our NRAC probe, as you can tell, is placed on top for readings in the chamber. So we have a video prepared of our methane hydrate in action.
I don't know.
Is it?
No, it's not PDF. What does it say?
It just says going on YouTube.
Potential security concern.
Oh no. Oh no.
So it's clown, displays clown.
That's okay.
Okay, so this is always good to try to it'll show here at this. Okay. Need volume?
No.
Okay.
So yeah, basically, as you can tell, the methane hydrate is in the combustion chamber. We first have to ignite it and then put the combustion chamber on, which is a design problem that we found out while doing this experimentation. So we definitely put that as a systems issue that we would like to fix. And as you can tell, also, the methane hydrate is difficult to ignite. One of them it couldn't be ignited, while the other one was, we were able to get data out of it. So to touch on our experimentation, we, from last quarter, we had a needs metric matrix where we had certain criteria that we needed to fulfill for this experimentation. So the first one that I want to touch on is laminar airflow. So we looked at the Reynolds number, and we have to make sure that it's less than 20. So this is important for our chamber because in order to get accurate emissions readings, we need it to be laminar flow, so that it can just be stagnant, the airflow could be stagnant, and all the emissions could be towards the top where the NRAC probe can measure it. Next, the measurement of the air inlet and the exhaust volumetric flow rate is important, because if there's any slight change or deviation in the airflow rate, then it can cause turbulent flow, which will result in inaccurate data. So that's why we have a really low marginal value for this criteria. And then lastly, for the water vapor emissions, we would like to figure, since methane hydrate is basically ice, or methane entrapped in ice, in order to melt it, basically to ignite it, there's a lot of water vapor that comes down from it, but we don't have a way of measuring it, so this is one of our criteria that we will be focusing on next quarter. And so with that in mind, we have some of the engineering principles that we implemented in order to figure out in order to, let me go back, to get these marginal values. So the first engineering principle that we implemented was the chemical equilibrium equations. So we have an unknown amount of our fuel, and from experimentation we were able to get results to get our these numbers, which are the coefficients, right? And so after you get the coefficients, you're able to use the mole ratio in order to get the airflow rate, and then the airflow rate in terms of liters per minute. So this is one of our criteria. This is how we found the airflow rate that goes into the chamber. The next engineering principle is fluid mechanics, which is getting the volumetric flow rate. We used Bernoulli's equation, and we made assumptions that the height is the same across the pipe because it's cylindrical. And then afterwards, we were able to get a volumetric flow rate and a pressure difference that we implemented into our chamber. And lastly, we have the Reynolds number is a criteria, like I mentioned earlier in the need metrics matrix, where it has to be less than 2100. And given these conditions, it would be less than 2100. So.
And then for the bill of materials, as you all saw through our SolidWorks schematics, most of our materials are being used from the lab, and most of them are not manufactured, mainly going to be bought. And at the moment, we have our strain gauges and flow meters on the way, which we hope to have soon, and use them to again do more tests when it comes to dry ethanol and then methane hydrate. And if all is successful, then this will be our finalized bill of materials.
So to conclude, some of the challenges that I already previously mentioned through the video is the fact that methane hydrate is difficult to ignite, so we have to figure out strategies to like breaking up the sample and allowing for warming time, preheating basically. Another issue is the fact that the airflow is too fast, so it extinguishes the flame of the methane hydrate. So there's a trade-off between complete combustion and laminar flow. So that's another issue that we have to address. And lastly, some structural issues are for the systems engineer to kind of find solutions for, which is the fact that in our combustion chamber we have basically everything is really tight fit. So we need to kind of readjust the design a little bit. And then also we don't have a source for the wires to kind of go out of the chamber, so we're going to have to implement that as well. So these are the things we're going to be addressing for the following weeks up until the next quarter. Thank you.
All right, nice.